airplane will perform best at sea level on a cool, dry day. However, anytime altitude, temperature, and moisture, or any combination of these three increase, the air is less dense and there are fewer air molecules available to generate lift. A good way to remember this phenomenon is by using the 3H method. High, hot, humid. These all contribute to high density altitude. Density altitude is the term used to describe the effect temperature and humidity have on performance of the aircraft. High density altitude decreases airplane performance, and low density altitude increases performance. Lift depends on the shape of the airfoil and the angle of attack, which is the area of the airfoil surface exposed to relative wind. Another aspect of lift is the density of the air in which you're flying. On hot days, the density of air is less than on a comparatively cooler day. On wet days, the density of air is less than on dry days. Also, remember that density decreases with altitude, and when the density of the air is thin, the lift will also be less. To compensate for this less dense air, the pilot would have to increase the plane's airspeed in order to maintain the same angle of attack. Density altitude is the main reason we use airplane performance charts. If all pilots could fly at sea level that was cool and dry, there would be little change in the performance of their airplanes. However, this is not the case, and pilots always have to deal with the effects of changing air density. Some other conditions that affect the airplane's performance are gross weight, headwind and crosswind components, and runway surface. To compute density altitude, we need to know the existing temperature and the pressure altitude. Pressure altitude is altitude adjusted for non-standard temperature and pressure, and can be read from the altimeter with the barometric pressure set to 2992 inches of mercury. You must have pressure altitude to determine density altitude. You can compute density altitude in several ways, one of which is a chart, which includes a table to determine the altitude correction necessary to find pressure altitude. The graph itself displays outside air temperature along the horizontal axis. Approximate density altitude along the vertical axis, and pressure altitude along slanted reference lines. For example, if the airport elevation is 3,165 feet, the outside air temperature is 93 degrees Fahrenheit, and the local barometric pressure is 3010 inches of mercury, what is the density altitude? First, convert the true altitude to the airport pressure altitude. To do this, refer to the density altitude chart. Under the column of figures titled Altimeter Setting, find the barometric pressure of 3010. Directly next to it, you will find the altitude correction minus 165. From the airport elevation of 3,165 feet, subtract the altitude correction factor of 165 to get the pressure altitude of 3,000 feet. Now enter the graph at the temperature value, 93 degrees, and proceed upward to the 3,000-foot slanted pressure altitude reference line. Move directly left from the reference line and read density altitude 5,750 feet. What does a density altitude of 5,750 feet mean to a pilot taking off at an elevation of 3,165 feet? It means that the airplane will perform as if it were at an airport with an elevation of 5,750 feet. Let's try another example. The airport elevation is 5,480 feet above sea level. The outside air temperature is 80 degrees Fahrenheit, and the local altimeter setting is 2990 inches of mercury. What is the density altitude at this airport? To begin, we must determine the altitude correction for non-standard pressure. The table shows that if the altimeter setting is 2990, we must add 20 feet to the airport elevation of 5,480 to get a pressure altitude of 5,500 feet. Now, to complete this second example, let's enter the graph at the temperature of 80 degrees Fahrenheit and proceed upward to the 5,500-foot slanted pressure altitude line. Move directly left from this intersection and find a density altitude of 8,100 feet. Let's try another problem. In this example, the airport elevation is 4,725 feet above sea level. The outside air temperature is 90 degrees Fahrenheit, and the local altimeter setting is 3020 inches of mercury. With these conditions, determine the density altitude. Again, convert the true altitude to the airport pressure altitude. Under the altimeter setting column, find the barometric pressure of 3020 of mercury. Next to it is the altitude correction factor of -257. Subtract this 257 from the airport elevation of 4,725 feet, and you get 4,468 feet pressure altitude. Enter the chart at the temperature value of 90 degrees Fahrenheit and proceed vertically up to the slanted pressure altitude reference line of 4,468 feet. Move horizontally left from the reference line and read the density altitude of 7,400 feet. Let's do one more. Suppose the elevation at the airport is 3,700 feet and the outside temperature is 5 degrees Fahrenheit. The barometric pressure is 2960 inches of mercury. Using this information and the chart on the screen, what is the density altitude? First, determine the altitude correction for non-standard pressure. The table on the density altitude chart shows that if the airport altimeter setting is 2960 inches of mercury, we add 298 feet to the airport elevation of 3,700 feet. The pressure altitude is 3,998 feet. Now enter the graph at the outside air temperature of 75 degrees Fahrenheit and proceed upward to the 3,998-foot slanted pressure altitude line. Move directly across the chart to the altitude scale and find the density altitude of 5,950 feet. Takeoffs and landings are directly affected by the winds, but winds are seldom direct headwinds, tailwinds, or crosswinds. Therefore, you need to determine both crosswind and headwind components relative to the runway planned for takeoff or landing. Let's look at a wind component chart to determine this information. Along the horizontal axis is the crosswind component, and along the vertical axis is the headwind component. The reference arcs are the wind velocity, and the spokes of the circle represent the angle between the wind direction and the runway. For example, there is a 20-knot wind at 50-degree angle to the runway. What is the headwind component and the crosswind component? Follow the 50-degree reference line to the 20-knot arc. Then follow the vertical line down to the crosswind component of 15 knots and follow the horizontal line to the headwind component of 13 knots. Let's solve one last problem using the wind component chart. Again, the maximum crosswind component for our airplane is 15 knots. The landing runway heading is 290 degrees, and the wind is 240 degrees at 25 knots. Can we safely land? Again, you must determine the angle between the wind and the runway heading. The difference between 290 degrees and 240 degrees is 50 degrees. Now enter the graph at the 50-degree line and proceed toward the center until reaching the wind velocity of 25 knots. Proceed left and read the headwind component, 16 knots. Then proceed down and read the crosswind component of 19 knots. Finally, compare the result, 19 knots crosswind, to the manufacturer's maximum allowable crosswind of 15 knots. The airplane should not be landed on this runway with this wind. You must either choose a different runway or airport or simply not fly. Now, before we discuss takeoff performance, you must have a good understanding of the difference between the best rate of climb airspeed and the best angle of climb airspeed. The best rate of climb airspeed provides you with the greatest gain in altitude for a given period of time. The best rate of climb speed is abbreviated V for velocity and small y. The best angle of climb gives the greatest gain in altitude for a given horizontal distance. The best angle of climb speed is V and small x. The importance of these two speeds is that Vy, the best rate of climb speed, is used after all normal takeoffs to gain altitude most quickly. But when there are obstacles at the end of a runway, you may elect to use Vx, the best angle of climb speed, so that you gain the greatest altitude before flying over the obstacles. These speeds can be found for any given airplane in the pilot's operating handbook. We use takeoff performance charts to determine two related and important numbers. These are the ground run to actually become airborne and the total distance required to clear a 50-foot obstacle. I might quickly add here that the type of runway surface has a direct effect on airplane performance. Soft grass, loose gravel, sand, asphalt, concrete, as well as snow or puddles on the runway are all factors that can have a pronounced negative effect on takeoff performance. The takeoff chart for the skipper looks like this. As you can see, it combines several graphs in one. It also contains, like most performance charts, extensive notes or associated conditions which must be studied in addition to the chart itself. To use this chart, we need to know the pressure altitude, outside air temperature, takeoff weight, wind component, and the obstacle height. Since this chart is titled Takeoff Distance, Hard Surface, we'll solve a problem for taking off on a paved runway with a temperature of 15 degrees centigrade, a pressure altitude of 5,650 feet, takeoff weight of 1,675 pounds, and a headwind component of 9.5 knots. What is the takeoff distance? And what is the distance required to clear a 50-foot obstacle? Simply enter the chart at 15 degrees centigrade. Follow the line almost to the 6,000-foot pressure altitude line. Then follow the horizontal line to the weight reference line. Your weight is 1,675 and your entry point to the chart is at 1,675 weight point. In this case, it is the same as the chart reference line. We then move horizontally to the wind component line. Parallel the closest dark diagonal headwind line to a point where it intersects a vertical line drawn from 9.5 knots. Then move horizontally to the height reference line. If obstacles, continue horizontally to read the ground run of 1,060 feet. If there are obstacles, parallel the obstacle height diagonal reference lines to the obstacle reference line and read the distance to clear a 50-foot obstacle of 1,750 feet. Let's now take a look at a similar example that involves the skipper taking off on a grass surface. The note under Associated Conditions tells us that this chart describes performance on a runway with a level, dry, short grass surface with a firm subsoil. As before, we will assume that the outside air temperature is 15 degrees Celsius, pressure altitude is 5,650 feet, the takeoff weight is 1,675 pounds, and the headwind component is 9.5 knots. As always, before attempting this problem, be sure to familiarize yourself with all the notes on this performance chart. Begin by entering the chart at the outside air temperature of 15 degrees Celsius and move upward to the 5,650-foot pressure altitude line. Then move right horizontally to the weight reference line. Since your weight of 1,675 pounds is the maximum takeoff weight for this airplane, simply keep moving horizontally to the right until reaching the wind component reference line. Your headwind component is 9.5 knots. So follow the solid diagonal headwind lines to the vertical intersection with 9.5 knots. To get the final answer, move from this last point horizontally to the right until reaching the obstacle reference line. If the takeoff is to be attempted with a 50-foot obstacle at the end of the runway, find the distance required to clear this obstacle by following the diagonal obstacle lines to the outside reference line, which is 1,900 feet. If this takeoff is without obstacles, simply continue horizontally to the reference line to find the ground roll of 1,240 feet. Here that in these examples, the distances were higher than in the previous example where the airplane was being operated on a hard surface runway. Another type of performance chart shows us takeoff distance versus density altitude. Remember, as density altitude increases, your takeoff distance will increase, and you will need more runway for your airplane to become airborne. If you have to clear an obstacle at the end of the runway, you will need even more runway footage to gain flying speed. This chart will help you compute the takeoff distance if you know the density altitude of the airport. The chart lists the density altitude figures in thousands of feet on the vertical axis and gives the takeoff distance in feet on the horizontal axis. There are two reference lines drawn inside the chart. One you would use to compute for takeoff ground run, and the other to compute the takeoff distance needed to clear a 50-foot obstacle. Let's solve some problems using this chart. If the density altitude at the airport is 4,000 feet, what is the takeoff distance needed to clear a 50-foot obstacle? Enter the density altitude scale at the 4,000-foot line. Draw a line horizontally to the 50-foot obstacle reference line, and where those two lines intersect, draw a line vertically down to the takeoff distance axis. Takeoff distance is 2,250 feet. If we just wanted to know the takeoff distance without the obstacle, the answer would have been approximately 900 feet. To solve this, enter at the 4,000-foot density altitude axis and proceed horizontally to the takeoff ground run reference line. Follow the vertical line down to find 900 feet on the takeoff distance scale. Another example using the takeoff distance versus density altitude chart is as follows. If the density altitude is 2,750 feet, what is the takeoff distance needed to clear a 50-foot obstacle? Enter the density altitude scale at the 2,750-foot line. Proceed horizontally to the 50-foot obstacle reference line. Now move down vertically to the takeoff distance axis. The distance to clear a 50-foot obstacle is 2,075 feet. If we had been asked for takeoff ground run distance, the answer would have been only 875 feet. Now we'll look at the other takeoff performance data in form to determine runway distance and obstacle clearance. This type of table has columns of numerical solutions for specific combinations of conditions. The notes tell you how to solve for conditions other than those listed, or you may need to interpolate or split the difference between the answers in the table. Using the takeoff data chart, let's find the total takeoff distance required to clear a 50-foot obstacle using this given information. Airplane gross weight, 2,000 pounds. The pressure altitude is 2,500 feet. The outside air temperature is 100 degrees Fahrenheit, and the headwind is 10 knots. Enter the chart at 2,000 pounds under the gross weight pound column. Move to the right past the indicated airspeed column, which tells you to use 63 miles per hour, to the headwind column. Use the 10-knot line. Work your way across to the two columns under 2,500 feet at 50 degrees Fahrenheit. The ground run is 530 feet, and the total ground run to clear a 50-foot obstacle is 1,005 feet. Because the outside temperature is not 50 degrees Fahrenheit, refer to note number 1. The note says to increase distance by 10% for each 25 degrees Fahrenheit above standard temperature. Since the distance required to clear a 50-foot obstacle at 50 degrees Fahrenheit is 1,005 feet, for our 100-degree temperature, you would need to add 20% more ground run to clear the same 50-foot obstacle. 20% of 1,005 feet is 201 feet. So the total distance to clear a 50-foot obstacle is 1,206 feet. We have already discussed the difference between rate of climb and angle of climb. Let's take a brief look at this rate of climb chart to see how we can determine actual climb performance. Rate of climb data can be found on a table like this. Like all types of performance, climb performance is affected by temperature. The pressure altitude is 5,000 feet. Outside air temperature is 71 degrees Fahrenheit. A gross weight of 2,300 pounds, and the indicated airspeed is 81 miles per hour. What would be the approximate gain in altitude in a 4-minute constant rate climb? To solve this problem, enter the chart at the 2,300-pound gross weight line and move horizontally to the 5,000-foot pressure altitude column. Rate of climb is 35 feet per minute. Since the outside air temperature is not 41 degrees Fahrenheit, refer to note number 3, which tells you to decrease the rate of climb 20 feet per minute for each 10 degrees Fahrenheit above the standard temperature. The outside air temperature is 30 degrees higher than standard. You should decrease the rate of climb by 60 feet per minute. Thus, the rate of climb is reduced and is 375 feet per minute rather than 435 feet per minute. Finally, to figure the gain in altitude in 4 minutes, multiply 4 times 375 to get a 1,500-foot increase in altitude. On this program, you have learned how to calculate pressure altitude, density altitude, crosswind and headwinds, as well as takeoff and climb performance. You are now ready to learn about cruise range, stall, and landing performance charts. That is what we'll be doing in the next program. Before enduring every flight, you need to determine your airplane's expected performance from the performance data in the pilot's operating handbook. The performance will cover all conditions that a pilot may experience, but by taking the information in the charts and making some allowances for special conditions when necessary, you'll fly with a greater margin of safety. On our last program, we solved